When I was a teenager in the 70s, my mom said I'm crazy when I told her that I want to build an AI, an artificial intelligence, that learns to become smarter than myself, such that I can retire. And then later, in the 80s, when I had become a computer scientist, my computer science colleagues also said that I'm crazy, because back then they said superhuman AI is never going to happen, or it will take thousands of years, but not within your lifetime. But then suddenly, in 2023, many of these colleagues who wrinkled their eyebrows at my old predictions, they have changed their minds, and now they are predicting that AGI, artificial general intelligence, may be close. And they are warning about the dangers of AI using old arguments from science fiction stories. Now, why is that? Because many of these computer scientists were impressed by ChatGPT and similar large language models. How many in the audience have any experience with these ChatGPT-like models? Anybody here? Yeah. Who is using them daily in his daily life? Yeah. How many people know that there is an artificial neural network in there which is driving all of that? Lots of experts. And how many people know what kind of neural network that is? Yes, what is it? It's a transformer. A transformer which was called transformer in a 2017 paper by Google. But long before that, in 1991, I had a special variant of a transformer, which is now called an unnormalized linear transformer. I didn't call it unnormalized linear transformer. That's what it's being called now. But the math is exactly that. And what is it about, this unnormalized linear transformer? It's just a network which has learned to program a part of itself by producing key patterns and value patterns such that there is a mapping, an attention mapping, as it is called now, which can then be applied to queries, and essentially, depending on the temporal context of the data which is coming in, you shift through this mapping your attention on the important parts of the data. So, that was a neural network back then in 1991, which was very nonlinear in many ways. And it's a little bit weird that now it is called a linear transformer, but the linear refers to this quality of scaling, because the traditional, or the new transformers, the modern transformers, they don't scale well. If you give them a text which is 1,000 times longer than before, then you need 1 million times more compute, 1,000 times 1,000, 1 million times more compute. And the linear transformers, they only need 1,000 times more compute, so they scale linearly, not quadratically. And that's, of course, quite natural, because back then, in the 90s, early 90s, compute was roughly 1 million times more expensive than it is today. So we had a great incentive to make everything as efficient as possible. Still, although we tried to do that, we could do only little tiny experiments, toy experiments, where queries are being answered by these fast-rate programmer systems, as I called them back then. But today, of course, we can do so much more. And that's because compute has become 1 million times cheaper. Now, whenever I'm boasting about our old achievements of 30 years ago, I have to think of that story of the two beavers swimming in this huge artificial lake. And one of the beavers points to the huge artificial dam. And the other beaver goes, "Wow, did you build that? And the first beaver goes, no, but I had the idea first. Now, back then, we couldn't do anything with our neural networks except for toy experiments. But since compute has become 5 times cheaper, 10 times cheaper every 5 years, now suddenly we can roll that out to billions of people who have stuff like that now on their smartphones. And the world is quite different, just through this acceleration of compute, which has applied to many of these old concepts of the 90s, when the basic foundations were laid for what's now on billions of devices. Now, back then, we also had other interesting developments going. In particular, in the same year, in 1991, the diploma thesis of my brilliant student, Sepp Hochreiter, came out. And that was about something which is called the vanishing gradient problem. Does anybody know what is that, the vanishing gradient problem? Yeah, some do. So there's a problem if you have really deep neural networks or recurrent networks, then they don't learn well because there is this problem which Sepp identified in his diploma thesis and overcame it through what is now called residual connections. 1991, and these residual connections, they were now then put into what in 1995 was called LSTM, long short-term memory. Has anybody heard of that, long short-term memory? Okay. So this is a publication. So the name I invented in 1995, but it goes really back to Sepp's diploma thesis of 1991. And then in 1997, we had this paper, the most well-known paper on LSTM, which today is the most cited AI paper of the 20th century. And it's also in your smartphones. Bloomberg called it the most commercial AI type, because it's doing speech recognition and machine and translation from one language to another. And Facebook, for example, already in 2017, they used it 4 billion times a day. Because isn't anybody on Facebook? Anybody on Facebook? Yeah. And so there's a little button, and you can translate the message from your Spanish friend. And 4 billion times a day already in 2017. Facebook did that. And the best thing was, every time you press the button, we got 1 penny. And so now we have a mountain of pennies, and we can afford a nice dinner every single day. Well, it's not true. I'm just kidding. Facebook, the sad truth about Facebook is they never gave us anything for that. They didn't even send us a thank you letter or something like that. The Facebook became valuable, I don't know, 600 billion or something like that, dollars on the stock market, not because they wasted money on stupid researchers funded by foreign taxpayers. They don't have to do that. Anyway, back then, also in around 1990, we had another thing which is really important in today's generative AI. So generative AI, who is familiar with that notion, generative AI, many newspapers talking about that. And back then, in 1990, we had this idea which has become very popular, which is you have not only one network, but 2 networks, and they are fighting each other. One of them is producing outputs. Output patterns can be anything, can be actions, can be anything. And then there's another network which sees the outputs of the first network as an input and tries to predict the consequences of the outputs of the first network. So it uses gradient descent, backpropagation, to make some of its internal connections stronger and some of them weaker, such that it becomes a better predictor of these consequences, of these actions. And over time, the error of that one is decreasing all the time. However, the first guy is trying to maximize exactly the same error that the other guy is trying to minimize. So the first guy is trying to come up with output patterns that are still fooling the second guy. So then you have this fight going on, and the first guy becomes better and better at generating more and more convincing output patterns that that still fool the second guy. I didn't call that generative adversarial networks as it is called now. I called it artificial curiosity. And it's useful for not just for making deepfakes and for making images that look a lot like as if they were real, although they are fake and made up. But they can also be used to make robots explore the world. So you have a robot that is trying to explore an environment, and you are generating actions, and the robot is executing these actions, and then something happens in the environment, and the second network is still trying to predict the consequences of the actions of the first guy, which means that the second guy is minimizing its prediction error, and the first guy is trying to generate experiments, action sequences that lead to data where the second guy still can learn something from. So artificial curiosity for robots is also one of the applications of this principle of the two fighting networks. And over the decades, we have produced many more sophisticated versions of that, which are now at least partially widely used, although they are not yet as popular as ChatGPT and purely supervised learning machines that just try to model all the existing human-generated knowledge in a way that is easily addressable by natural language. So what ChatGPT is doing is a fine way of indexing all of human knowledge in a way such that you can easily address it through natural language questions and can easily retrieve answers in this way. And it's totally based on supervised learning. You just look at lots of data, and you try to predict parts of the data from other parts of the data. But it's not in any sense creative, as you would like to see in truly creative systems, which see new patterns in the data from the environment. It doesn't even learn. So it once learns in a supervised way, and then it can be used in many good ways, and it can summarize documents that it sees in a particular style, and other similar systems, they can generate images in a particular style, and in Van Gogh-like style, for example. But all what they do is they retrieve existing knowledge, existing styles invented by Van Gogh and other people and so on. But it's also possible to build these truly creative systems which generate their own experiments, which lead to data where you see patterns in the data that you didn't see before, and then they learn that, and they get a joy feeling, an internal joy moment through discovery of some new scientific law, where you see a pattern in the existing data, which just means that you can more compactly encode the data that is coming in than before. For example, if you see a video of falling objects over the time, or you cause the video of falling objects, then over time you see how these objects accelerate always in the same way, which means that you can predict parts of the movie of these falling objects from other parts. So you see 3 pictures in a row, and you can pretty well predict the 4th picture, which means that you can better compress the video, because everything that you can predict, maybe you cannot predict everything, but everything that you can predict can be used to compress the video. And if you look back at the history of science, it's a history of compression progress. And one can implement that in curious systems that learn to generate experiments that have the property that they generate data from which the prediction machine can learn regularities that it didn't know before. So you have these artificial joy moments for these artificial scientists that are that are inventing their own experiments to understand better what's going on in the world and what can you do and what kind of problems can you solve with your own actuators in a world that is working like that. How many more minutes do I have? I think it says something. 16:55. All right. Now, as we have seen before, much of what is working so well now is based on stuff that is old from the previous millennium and actually deep from the previous millennium. If you look at all this deep learning stuff, which is currently so popular, it goes back hundreds of years. The first neural networks were not published in 1950 or something. No, they were published in 1800, around 1800, because back then, Legendre and Gauss, they published what's now called linear regression. They called it the method of least squares. It's exactly a linear neural network. Exactly the same error function, exactly the same connections and the weights on the connections that you adjust to minimize this mean squared error. So all of that is an old hat, and for deeper networks, everybody is using the gradient descent rule of 1676, when Leibniz really showed how to compute the derivative of something that is deep in the network with respect to the output. So this chain rule that was published in 1676 is central for all of what we are calling deep learning today. And the guy who made it efficient for deep networks was in 1970 Seppo Linnainmaa, the Finnish guy who developed or published first the thing which is now called backpropagation, modern backpropagation. Yeah. So now the nice thing is that this old trend, 5 times or 10 times cheaper computers every 5 years, it was already old in 1986 when I wrote my diploma thesis on meta-learning, on learning how to learn. And it goes back at least to 1941. 1941, that's when Konrad Zuse built the first program-controlled general-purpose computer, 1941. And this computer could roughly do 1 instruction per second. But then 5 years later, you could do 10 instructions for the same price. And today, or in 1986, when I wrote my diploma thesis, we already had gained a factor of 1 billion. I could do 1 billion instructions for the same price. And back then, for the first time, we had these desktop computers, which allowed us to do experiments that seemed infeasible just a few decades earlier. But it was still tiny, tiny, tiny compared to what we can do now. And today, we have gained another factor of 1 million. And by 2041, so 100 years after Zuse, we will have gained a total factor of 1 billion times 1 billion instructions per second for the same price. So in the near future, we will have neural networks, artificial neural networks, that are going to compute much more than any human brain, and probably also more than all human brains taken together. And everything is going to change. We are just at the beginning of a development which is going to take over everything. It's going to change all of civilization completely. And in 30 years from now, we will look back at today, at the year 2023, and we will say, oh, historically interesting, there were these things like ChatGPT and language models based on even older systems from the previous millennium, and they were already considered impressive. But 30 years from now, people will smile at these primitive applications because they will have so much more advanced stuff. And the nice thing, which is finally leading to the title of my talk, AI for All, which is the motto also of our company, NNAISENSE, this AI for All is becoming truth. Because already the methods that we have developed over the past few decades, they are used every single day to make human lives longer and easier and healthier. It's already happening. Communication barriers are breaking down because of these methods. There was a time 10 years ago when I went to China, and I had to show the taxi driver a picture of the hotel where I wanted to go. Otherwise, he wouldn't have understood what I wanted. But today, or a couple of years later, he just took out his smartphone and he spoke into it in Mandarin, and I understood the translation and talked back, and he understood the translated message. And so suddenly we can have conversations through smartphones in a way that is really breaking down communication barriers, not only between people, but between entire nations. So AI is really improving lives in many, many ways, and it's used like crazy in healthcare. If you look at LSTM applications in healthcare, just use a Google search in Google Scholar and try to type LSTM plus something from medicine, maybe diabetes. And you will get lots of articles which have this combination in the title, not just somewhere down there in the text, but in the title. And the same is true for arrhythmia, and all kinds of diseases which are treated with AI based on this. These neural networks that have been developed mostly, not totally, but mostly in the previous millennium, with epsilon improvements here and there, also in the post-2000 world. So AI is truly for all. It's not going to be for just a few companies. I'm always willing to sign letters of the open source movement, which says don't stifle innovation by closing down or regulating too much the open source community, which is maybe just 6 or 8 months behind the famous large companies in terms of developments of large language models and everything. And there is no moat, as somebody wrote. I think a guy from Google wrote, there's no moat for Google when it comes to developing such systems, because the open source movement is really close behind. So I'm very optimistic towards the development with regard to the future developments of AI, and everybody is going to have lots of AIs in his life which are going to solve all kinds of problems, and in fact, even much more than today, will help to make his or her life longer and healthier and easier. I think I have to finish very soon. Could that be? Is there anybody who wants to give me a sign whether I should? Oh, there's my sign. Okay. So I have still a few minutes, which means I can use that time to thank the organizers of the CogX organization, who have been doing a great job. A couple of months ago, when CogX contacted me for the first time and invited me to give a keynote here, of course, we also discussed the question of the fee. And the organizer said, we are going to be really strict here. 100,000, that is our last word. And I said, okay, give me 2 weeks and I will send you the money. Thank you very much for your attention, my lovely audience.